Well, thanks to everybody on Zoom and YouTube and all the people that have come from the meetup group. And it's great to have you all in here. And again, we do this every month. And this month, we're very pleased to have Alex Filippenko. He's an elected member of both the National Academy of Sciences and the American Academy of Arts and Sciences. He's one of the world's most highly cited astrophysicists, as you all know, and he was the only person to have been a member of both teams that revealed the accelerating expansion of the universe. That was a discovery that was honored with the 2011 Nobel Prize in Physics to the team's leaders and the 2015 Breakthrough Prize in Fundamental Physics to all team members. He was voted the best professor on the UC Berkeley campus a record 9 times. In 2006, he was named the Case Carnegie National Professor of the Year among doctoral institutions. And he has produced 5 astronomy video courses with the Great Courses, co-authored an award-winning astronomy textbook, and appears in more than 120 television documentaries. He's an avid tennis player, hiker, skier, whitewater rafter, snorkeler, and scuba diver. He enjoys world travel, and you know, if he could have been, he would have seen this eclipse too, and we were talking about that earlier. And in fact, he's seen 17 of them so far. Won't you please welcome to the Westport Astronomical Society, Dr. Alex Filippenko.
All right, thank you, everyone. Can you hear me? Yes?
Yes.
Boy, those are amazing photographs that your members have been taking. Congratulations.
Thank you.
And that's really, really impressive. Yeah. And then I snuck out for 5 or 10 minutes to take a look at Jupiter and Saturn. I was away a bit longer than I thought I would be because there are some clouds floating through and I needed to wait until the cloud cleared away. And earlier, when I was talking to Dan and Alex and others, and I went to grab a bite to eat, it was still a little bit too bright outside. So I only had a narrow window. You know, as you know, they set pretty soon. So, well, for you guys, they've already set. Mm-hmm. But anyway, it's certainly a pleasure to be here. Yeah, the eclipse was a real bummer. We were discussing before the meeting actually started that I would have been on a cruise in the South Pacific with my family, and that got canceled. And although Chile was rainy, the spot we had targeted for the South Pacific was clear. You know, not that it matters, right? In the end, we didn't go. So whether it's clear or not clear doesn't really matter. But I know that the people who were going to go to Chile were at least a little bit relieved that it was cloudy. Not that they wish the residents of Chile and the people who were down there bad skies, but just it was a bit of a, you know, a softening of the blow, so to speak, because I know a lot of people whose trips to Chile got canceled. Yeah. But yeah, Argentina was clear, and there's some live feeds that are now recorded. At the beginning of the chat, I listed a Facebook address.
I just reposted it again for you, Alex.
Yeah. Okay, so that was taped. That was with Wilderness Travel. So I gave a little 40-minute lecture on eclipses. Then I did a commentary on the eclipse as it was happening. And then I answered questions for another 45 minutes or so. So if you wish, you can take a look at that. But it was sponsored by a company called Wilderness Travel, with whom I was going to travel to the eclipse. So anyway, yeah, I see you put it. Let's see. I see the chat here. Yeah, 2024 beckons. That's true. There's, of course, 2021 in Antarctica, about the same time of the year, December 4th, 2021 is the eclipse. And then there's a hybrid in April of 2023 in Indonesia. But most of it is total, just the very ends are annular. And then there's 2024, you know, which should be easy for most of us. Although I don't know, if I were in the Northeast, like where you guys are, I might consider going farther down south to Texas or something. But look at Jay Anderson's forecasts. They're usually pretty good. Okay, well, listen, why don't I share my screen, which I can then point to my PowerPoint presentation. And we thought that I'd do a pretty extensive Q&A at the end. And you can, you can ask a question during the presentation, but it's likely to be something that I'm going to cover anyway. So maybe just wait, unless it's something that's completely confusing, and you need me to stop, that would be okay. But I will do an extensive Q&A until about 10 o'clock your time after my presentation, okay? So, but just, I don't know, let's see if I have the, if I put participants, I think if you raise your hand as a participant, then if you really need to ask a question during the talk, I'll see you and I'll call on you or something. So, okay. So yeah, I want to tell you not only a little bit about the history of the discovery of the accelerating expansion of the universe that was mentioned in your kind introduction, but also give you a new surprise, which you may or may not have heard about. It's been gaining traction now for a couple of years. The statistical significance is getting stronger and stronger. And so there are more and more news articles about it. Just to spill the beans to those of you who might need to go to bed early or something, even taking the acceleration into account, the known acceleration, what we've been finding with our latest measurements is that the current rate of expansion, the so-called Hubble constant, is bigger than would have been anticipated. And in particular, it's bigger than what you get if you take measurements of the early universe through the cosmic microwave background radiation, the afterglow of the Big Bang, and extrapolate to 13.8 billion years later till now, you can predict what the current Hubble constant should be. And they get, something like 68 kilometers per second per megaparsec. And we, making measurements with supernovae, get 74 kilometers per second per megaparsec. And the statistical uncertainties are sufficiently small that this really looks to be a cosmological conundrum now, not caused by an error on the part of the measurements of the cosmic background radiation or measurements of the present day universe. So that in a nutshell is what I'll tell you about near the end, okay? But in case you want to leave and you already know about the accelerating universe, well, that was the bottom line. Okay. All right. So the story begins with Vesto Slipher. I mean, I know you're all astronomy enthusiasts, so I don't have to go into as much detail as I do for the typical public talk. But, just to be complete here, I feel that Slipher doesn't get nearly the credit that he deserves. Everyone's heard about Edwin Hubble, but Slipher really came up with half of the data that Hubble used. Slipher looked at galaxies like the ones you've been showing in your beautiful pictures, and he took spectra of them, and he noticed that the patterns of absorption lines were the same as in laboratory gases or in the sun or in a star cluster, but shifted to longer wavelengths in most cases. Andromeda Nebula was blue shifted, but most of the others were redshifted. But he didn't have the distances of the galaxies, so he couldn't really do much with this observation. So then along came Edwin Hubble, who, using the famous 100-inch Hooker telescope at Mount Wilson, which I had the privilege of using for part of my doctoral thesis at Caltech. It's an amazing instrument. I got a chance to go back about a year and a half ago when someone was doing a documentary about the first 30 years of Hubble. So they brought me to Mount Wilson to talk about the early history of cosmology. I still haven't seen the show. I've heard that it's a good show, but anyway, I was there for like 15 hours, and I think they had me on for only a minute or two, but I guess they had a lot of material to cover. Anyway, that's how it is with these documentaries. There's hours and hours and hours of filming for what is very little screen time. But anyway, I got a chance to relive my grad student days by gazing at this amazing instrument. But as most of you know, Edwin Hubble looked at the Andromeda Nebula, which was not yet known to be a galaxy. And he took repeated photographs of it, and he found a bunch of novae, stars that brightened but were already there. And then he found one here that he thought was a nova, but then in earlier pictures, he could see that there was a faint star there that had simply brightened. Whereas the novae, before they brightened, they were too faint to be visible at all. They're white dwarfs, basically, in binary systems. So there was nothing there, and then they brightened. But here he noticed that there was something there, and then it brightened, but not as much as a nova. So he called it a variable star, and he realized that it had the light curve, the brightness versus time, of a typical Cepheid variable. Now, these objects were known to be quite luminous, and Henrietta Leavitt at the Harvard College Observatory had studied a bunch of them in the Magellanic Clouds. Harvard had a southern observatory, an outpost there. By the way, you guys mentioned Helen Sawyer Hogg, who also studied variable stars. And indeed, she studied R.R. Lyrae stars, which are dear to my heart because R.R. Lyrae stars in the globular cluster M15 constituted my first research project. But anyway, Henrietta Swan Leavitt looked at Cepheid variables in the Magellanic Clouds, and she noticed that there's a period luminosity relationship. The more luminous ones are also the ones that have a longer period, and the ones that are on average less luminous have a shorter period. So that meant that all you had to do was measure the period of a Cepheid variable of unknown distance, measure its average brightness, and compare that with the average luminosity or power of a Cepheid variable having that period, okay? And doing that would then let you determine the distance of the Cepheid variable and the cluster of stars that it's in, or the galaxy that it's in, or whatever. And again, it's just like judging the distance of an oncoming car by looking at how bright the headlights are. You gauge the true power of the headlights for a car of known distance, a couple of meters away. Well, those are pretty bright headlights. And then you look at cars that are farther away and you see that the headlights look dimmer. So your brain, almost intuitively, almost instinctively does this measurement using the inverse square law of light, of course. But it's almost instantly giving you the distance. I like to joke that if you're not very good at doing this, you shouldn't be driving at night. Now, the angular separation between the two headlights gives you a consistency check. Your brain does compares the two measurements, which, by the way, is why it's harder to judge the distance of a motorcyclist, because there's not a pair of headlights. Anyway, stars, cars, all the same thing. And so, Hubble found Cepheids in this Andromeda galaxy, and my credit got cut off here. It's Adam. Oh no, it was just cut off by my zoom bar. Adam Evans took this photo. I'm sure some of you have photos that are of comparable quality. But as you know, to go out to the farthest reaches of the Andromeda Nebula, it's like 6 full moon diameters. It's incredible. But anyway, Hubble found Cepheids, realized they look really faint, but they didn't look redder than normal, like a red setting sun. So he deduced that they're faint not because there's dust in the way, but because they're distant. And thus the Andromeda Nebula is distant. And given its angular size, 6 full moon diameters, although I don't think Hubble knew that, but he knew it was big, he reasoned that it had to be an external galaxy. So figuratively, in 1923, Hubble expanded our universe. And then, of course, he looked at other galaxies whose redshifts had been measured by Slipher. And Hubble measured the distances of these other galaxies, again, using Cepheid variables. And he found this most important relationship that, most of them are moving away, but the more distant ones, here's some in the Virgo cluster, are moving away more rapidly than the nearby ones. And, he used the redshifts that Slipher had determined, but in his research paper, Hubble did not cite Slipher. These days, that would be grounds for dismissal from a university, even if you have tenure, to be using someone else's data without proper attribution is terrible. Hubble actually did a bunch of rather nasty things like that. He's this American astronomer hero, And sure, he did some really good stuff, but there's a lot of things he's given credit for that aren't entirely his. I'm sorry if he's totally your hero. Everyone has their faults. We're all human. Hubble had a number of faults, but anyway. But there's his original plot where he had speed in kilometers. Now we know he meant kilometers per second, but if you look at his plot from the Proceedings of the National Academy of Sciences, here it is. Speed versus distance in parsecs. A parsec is about 3¼ light years. So yeah, there's a correlation here. The open and filled symbols are just somewhat different measurements or something. I don't know, maybe galaxies in clusters versus galaxies not in clusters. I'm not sure. Anyway, it did take a bit of a leap of faith to think that there's a real correlation here. And in fact, Hubble resisted for a long time the modern day interpretation that this is caused by an expansion of the universe. His original data would fall in that lower left-hand corner square there. Here's a more recent diagram based on supernovae, which I'll discuss much more, type 1a supernovae. This only goes out to 2 billion light years, 700 megaparsecs. The research I'll tell you about today goes out to 10 billion light years. And we have a very nice Hubble law. All right. So here it is. V, the speed of recession, is proportional to the distance with the constant of proportionality, possibly changing with time, but at the present time, it's got a value h naught. That's what the subscript 0 means. At the present time, everywhere in the universe, it's thought to be the same value, but it can and does change with time. So many astronomers prefer to call it the Hubble parameter. Now we call this the Hubble-Lemaitre law, because there was a Belgian priest / astrophysicist, Georges Lemaitre, who 2 years before Hubble's discovery basically had the right answer using previously published data. He published his paper in an obscure Belgian journal. He then translated it for the monthly notices of the Royal Astronomical Society in England. But that was some years later, and he left out the crucial paragraph that talks about the Hubble law, the Lemaitre law. He didn't really talk about that part in his translation. Unclear why. Anyway, for a while, it was thought that there's some conspiracy theory that the translator may even have been Hubble, who intentionally left out that crucial part of Lemaitre's paper. But I think Mario Livio or someone else did a very careful study of this and found in his own handwriting Lemaitre's defense of this, that it had already been published by Hubble. But it wasn't at the time he originally published his paper. Anyway, the American Astronomical Society and the International Astronomical Union decided to give credit to Lemaitre and to call this now the Hubble-Lemaitre law, although the Hubble constant is still called the Hubble constant because Lemaitre didn't really talk about that in his paper. Okay, so the modern day interpretation is that this is caused by an expansion of space itself. And the wavelength of light, light isn't bolted down to the fabric of the universe the way a light bulb is or an observatory is. So the electromagnetic waves can expand. And that's the origin of what we call the cosmological redshift. It's not a Doppler shift. A Doppler shift is caused by the motion of an object through a pre-existing space, okay? This instead is an expansion of space. And you might think that we're at the middle because we see all these other galaxies moving away from us. So, what is it? Are we really that important? Or do all these other galaxies not like us? Is it something we said, or do we smell? Are all these other galaxies lactose intolerant? Get it? Milky Way galaxy, lactose intolerant galaxies. Or when I teach about cosmology to my class at Berkeley, I say, what's the problem? Are we from Stanford or something? with due apologies to those of you who might be Stanford alumni or who have friends or relatives who went to Stanford. It's an outstanding institution. It really is. I tip my hat. It's just not as outstanding as Cal. Anyway, no, we don't think we're at the center. Here's, a nice analogy, an expanding loaf of raisin bread, where the dough is uniformly filled with yeast, and you let it sit for an hour, and the whole thing expands. And regardless of whether it's finite or infinite, from any raisin's perspective, all the other raisins are moving away. And moreover, since there's yeast in all parts of the dough, every inch turns into 2. Every centimeter turns into 2. So a raisin that started 5 centimeters away after, say, 1 hour is 10 centimeters away. It moved with an average speed of 5 centimeters per hour. But one that started 10 centimeters away and ended up 20 centimeters away moved at an average speed of 10 centimeters per hour. So that agrees with the observation that right now at a given time, the more distant galaxies are moving away faster than the nearby galaxies. Okay. All right. Well, I'll have more to say about the Hubble constant near the end of the talk. For now, though, you might think, well, Hubble, Lick Observatory, Keck Observatory, we've all measured the Hubble constant, so we're done. Cosmology is done. But cosmology isn't done. And this goes all the way back to Newton, who supposedly saw the apple fall from a tree and wondered whether the force or whatever it is that causes the apple to fall is somehow related to the moon keeping its orbit around Earth, staying with Earth, even while Earth orbits the sun. And of course, he came up with his laws of motion and his law of universal gravitation, which are well known. But the law of universal gravitation is universal. Galaxies should be pulling on one another. So if you've got one cluster of galaxies here and another cluster over here somewhere, they should be pulling on one another. The universe should be decelerating. And if it's slowing down enough, that is, if the density is sufficiently high, it will someday stop and then recollapse. Big Bang, Big Crunch, or Gnab Gib, which is Big Bang backwards. So if you were watching galaxies in a universe like that, you would see them getting fainter and smaller, and you'd say, well, I live in a good, well-behaved universe. But then you'd notice something sort of peculiar. And right around now, you'd get kind of nervous, and then, goodbye, cruel world, right? The universe would collapse in on you. You'd be crunched and fried. So that's one possible fate. But it could be that the density of the universe is not sufficient to ever stop and reverse the expansion. It could be not like a ball tossed gently, but rather a ball, attached to a rocket, or a rocket launched at greater than Earth's escape speed. If the Big Bang launched the universe faster than its escape speed, then it'll never stop, or even if it stops just barely, it'll never recollapse. So in that kind of a universe, the expansion is eternal, and the universe continues to get ever colder, darker, more dilute, a very different fate than the Big Crunch. So astronomers, cosmologists want to know, just because we want to know what the fate will be. And just as you could look at an apple or a ball that you tossed and measure its speed at many different times and see whether it's been slowing down a lot, in which case it'll stop and reverse its motion, or not slowing down a lot, in which case it'll continue forever, so too, you can examine the past history of expansion in order to determine the fate of the universe. And the way you look at the past history is by looking progressively farther away. We see the sun as it was about 8 1/3 minutes ago. We see even the nearest stars as they were some tens or hundreds of years ago. We see galaxies as they were maybe 1 billion years ago, 4 billion years ago. Maybe that little blob there in the Hubble ultra deep field, that might be a look back time of 9 billion years. So we're seeing them as they were, and encoded in the light is information about how much the universe has stretched during the time the light has been coming toward us. That's the redshift. So if you measure the function redshift versus look back time, that function will be different depending on which kind of universe you live in. One that will eventually recollapse or one that expands forever. Okay, you can figure it out. The key is getting the distances and hence the look back times and comparing that with the redshift. Here it's not fair to use Hubble's law, measure a redshift, and derive the distance. No, because then that would be a circular argument. You need to measure a redshift and in an independent way measure a distance and then look for deviations in the Hubble's law. That's the name of the game. So you have to look billions of light years away, okay? Cepheid variables aren't luminous enough. The most luminous Cepheid variables are about 10,000 suns. Those are the 100-day long period ones. But 100,000 suns isn't sufficient to see galaxies that are billions of light years away. So you might want to give up. But no, don't give up. Damn the torpedoes, full speed ahead. Supernovae are a small minority of stars, but they literally blow up at the end of their lives, becoming millions or even billions of times as powerful as the sun. And many of you will recognize this. This is supernova 1987A in the Large Magellanic Cloud, okay? So here's one where we've sped up the process. They take, for the case of a 1A, 2 weeks to brighten and many months to fade. But here you're seeing a galaxy of 100 billion stars. And at its peak, that one star is the equivalent of several billion suns. It's as bright as the central regions of that galaxy. So if our sun were to do this, and don't worry, it won't. Sunblock of 50 just wouldn't cut it, folks. You'd need sunblock or supernova block of 1 billion or so to protect yourself. But our sun isn't going to do this because although it will turn into a white dwarf, it won't be a white dwarf in a binary system. And what you need is for it to be in a binary system. More on that in a minute. So let's look at supernovae and spread out their light in a spectrum. Plot the brightness versus wavelength. Blue is at about 4,500 angstroms. The red that your eye sees is around 6,500. Here's the near infrared. Here's the near ultraviolet. But anyway, they come in a number of forms, but the most common ones are of two types. Type 1, which don't have hydrogen, and type 2, which do have hydrogen, the most abundant element of the universe. Okay. And the type 1As in particular are those that have this deep line of silicon. There are other guys, 1Bs, that have lines of helium, and 1Cs that are distinguished from 1Bs in other ways. They don't have helium lines. Anyway, the 1As have been of greatest cosmological utility for the following reason. Not only are they luminous, a couple of billion solar luminosities, but they're pretty standard. And that's because they come about when you have a white dwarf gaining mass in a binary system. And that white dwarf could undergo nova explosions on the surface. That would leave the white dwarf intact. But somehow, some white dwarfs are able to escape the nova process and grow close to their maximum mass, known as the Chandrasekhar limit. And at that point, a thermonuclear runaway ensues. And it happens at 1.4 solar masses. So they all go off in roughly the same way. Not exactly the same way. And we had to calibrate that. I don't have time to go into it. Maybe in the Q&A I'll do it. But they're pretty standard. And they are standardizable. Now, they can also occur when two white dwarfs merge. One of them gets disrupted, material settles on the other one, and that other one still blows up at about 1.4 solar masses, even if the sum of the two masses was originally more than 1.4. The point is that the excess mass has not yet accreted onto the white dwarf, and that's why it blows up at 1.4. So they're pretty similar in how they explode and the mass at which they explode. And they're the most luminous of the typical supernovae. There are some more luminous examples now known, weird ones, but they're not as abundant. They're not as frequent, okay? So here's one in a nearby galaxy that my group actually found with a prototype telescope that we were developing for what then became our Lick Observatory supernova search. This was at an observatory near Berkeley called Leuschner Observatory. But we found 1994D in this really pretty galaxy, NGC 4826 or something like that. I don't remember. But here's a Hubble picture of it. Okay. So, as you know, supernovae are pretty rare. Maybe, 2 or 3 times per century per Milky Way galaxy, but most of those aren't even a 1A. A 1A occurs once every few centuries. But the type 2s occur a couple of times a century. So if I were a really cruel advisor, I'd have each of my students looking through the eyepiece of a telescope, like the great James Lick refractor, at one and only one galaxy until they find a supernova, and then we let them graduate and move on to greener pastures. Well, there are some crimes that are so egregious that even a tenured professor can and should be fired, right? We can't take advantage of students in that way. We could have them look at thousands of galaxies. That would improve their odds. But look, students need to study, sleep, and most importantly, at least before COVID-19, party, right? Maybe now they're having virtual parties. So that would be grounds for expulsion as well. Fortunately, with modern detectors, which you are all too familiar with, we have a better technique. You attach your CCD or CMOS detector to the eyepiece end of a telescope, take photographs of thousands of galaxies, and then simply look for arrows. And where you see an arrow, you see an exploding star. Look, it happened once, twice, 3 times, 4 times, 5 times. By rigorous mathematical induction, I conclude that it must work every time. Well, obviously it doesn't, otherwise we wouldn't give degrees for this kind of work. What we've done is we've developed a relatively small telescope at Lick Observatory, which was programmed to look at more than 1,000 galaxies a night. It's got a duty cycle of about half a minute or so, 25 seconds. And it then, compares the new images with the old images because it keeps on repeating the same galaxies night after night. And usually there's nothing new in the new image, but occasionally there is something new, that arrow. Well, we put in the arrow with Adobe Photoshop or something, but there it is. And, this is an area where amateur astronomers have contributed a lot. I've worked with many amateurs who found supernovae that ended up being very interesting, and they had early time data on those supernovae. And so in some cases, they were even co-authors on our papers. Now there's some wide angle surveys like at Palomar, the Zwicky transient facility that looks at these, 40 square degree swaths of the sky. They're finding most of the supernovae. Amateurs can still do really great science, citizen science with, exoplanets and asteroid occultations. In fact, with Shannon and Dan and others and Alex, I was talking before the meeting started that this new EV scope by Unistellar is really amazing for citizen science. And I'll put in the chat my email address. You can email me if you want the special code. I know the former postdoc at Berkeley, who was one of the co-founders of the company, and he gave me a referral code where it will give you 10% off and a 1 month advancement in the queue because there's a waiting list. And Sky and Telescope just had a review of it, a glowing review. I've heard, I haven't read it yet, but I think there were a couple of quotes from it that this is a game changer. So the number of people buying one will probably quickly rise. So being ahead in the queue might be useful. Remind me and I'll type in my email address. But anyway, in the early days, we were pretty competitive. We found more than 1,000 supernovae. Now we do mostly follow-up observations. But I have this team that now helps with the Zwicky transient facility. But here they were pre-COVID-19. And these kids, these college students, get so much of a joy, so much of a kick out of helping to discover a supernova. And they go on to fields that are not necessarily, professors of astrophysics, but that's okay. They're more likely to go on into fields that are more immediately useful to society, like medical physics and applied physics and computer science and engineering. And they get their hands dirty with real data analysis and statistical techniques and stuff. So some go on into astrophysics. This guy, I just finished writing letters of recommendation for him. With him, we just submitted 2 papers this week. He's one of the most phenomenal undergrads I've ever had. And, Julia is in grad school now. Sammy's in grad school. This picture was taken a year ago. Shaunak is another fantastic applicant. Anyway, they're amazing. And I get such a thrill out of helping, the careers of youngsters like this. Now, before COVID-19, we would have weekly group meetings where I would provide the pizza and they would justify their existence for the previous week. That's a fair trade, huh? Now we have, no pizza because we have group Zoom meetings. I don't know why my June 5th ended up being so small there. Anyway, so I don't provide pizza anymore. Maybe I will once we have our vaccine. But these students also then do follow-up observations with the 1 meter telescope at Lick, where it's not a big telescope by today's standards. It's not the Hubble. So we get lots and lots of time on it. And we get lots of time on the 3 meter telescope at Lick to get spectra. And we're very all cooperative. I can call up someone who doesn't study supernovae and ask for a favor because, we get lots of time. And now the campus observing rooms have led to a big increase in student involvement because students don't have to go to the observatory anymore, which is great because students typically don't have cars and they can't rent a car. And from anything other than the Santa Cruz and Berkeley campuses, you'd have to fly to San Jose and then drive up to Lick. And then you'd miss a lot of classes. But now we have these rooms set up at each of the University of California campuses. In fact, now during COVID-19, we've set it up so that people can observe from home. They can do the software from home now. So that has led to a big increase in student involvement as well. So it's just fantastic. They use the 3 meter telescope. They use Kate. They use the 1 meter telescope, which isn't in this picture. They use this thing called the automatic planet finder. I don't do exoplanets, but they're still really cool. Anyway, Lick is very dear to my heart. And I just wanted to mention just very quickly that University of California funding right now is uncertain, especially since the state legislature has told us that we're going to undergo another 15% cut because the California budget is just in shambles right now, in part because of COVID-19 and stuff. So I got a gift from Google, and I'm trying to raise matching private donations now. Through small amounts or big amounts, no donation is too small. And the more I get matching donations, the more they're likely to give me a renewal, which I'm just writing the proposal right now. And the matching donations can also be used for student and postdoctoral fellowships, if that's what, what gets you excited. But anyway, if you're interested, you can go to a site called give.berkeley.edu and just put Lick in the search box. Like the UC Berkeley, giving site. It's that. But anyway, or contact me. Oh, there's my email address in case anyone wanted to take a screenshot and contact me about the EV scope or anything else, or any questions that I don't happen to have time to answer tonight. Okay, so there's my email address. Anyway, back to cosmology. All right. So we found and studied a bunch of these nearby ones. So then the idea is go find and measure the brightness of distant ones. The apparent brightness will give you the distance and hence the look back time. And the redshift will give you the other variable in that function that we're trying to get, redshift versus look back time. Those are the two things we need. So we first have to find very faint, distant galaxy, supernovae, type 1a. And that we did mostly in Chile using the 4-meter telescope, which had a wide angle camera that takes a picture roughly the size of the full moon. So here, nearly every fuzzy blob is a galaxy. If you look away from our own Milky Way galaxy plane, you rapidly run out of galaxies. I mean, look at the Hubble Deep Field, things like that. I'm sorry, you rapidly run out of stars in our own galaxy, and you get dominated by other galaxies. So there's thousands of them here. Take 50 such pictures of different parts of the sky, you will have taken the mugshot of 100,000 galaxies. Repeat the process 3 weeks later. Even if type 1a supernovae occur only once per 500 years per typical galaxy, with 100,000 galaxies, there's going to be dozens of 1As there. So here's a subset, a sub-image of one of these wide-angle images. These are real data. You subtract the earlier data digitally from the later data, and you get noise. That's okay. Any measurement process necessarily has some noise associated with it. But here, cleverly placed in the middle of the square is something that looks like it might be real. And a Hubble picture of it a few weeks later shows it again, and it's marked with an arrow. So you know it's got to be a supernova. You got to still make sure it's a type 1a, and you got to get a spectrum. That's where my role came in on both teams. I have access to the 2 greatest optical telescopes in the world as a University of California faculty member. I'm a trained spectroscopist, and I've been doing supernovae since 1985. So both teams wanted me. And so I would get spectra of these things with the Keck telescopes. And there's Fred Chaffee, a former director, just showing you how big this monster is. I still have to pinch myself that I have the privilege of playing with this amazingly incredible and expensive toy instrument. I shouldn't call it a toy, but you know what I mean. You guys are all, many of you like playing with your telescopes, and I have liked playing with my telescopes since I was 14 years old. I got into it through the amateur astronomy perspective. So to me, it's just, I'm still an amateur astronomer at heart, and I get to play with this toy that costs $70 million. But anyway, we get spectra. And again, here's brightness versus wavelength. And here's a low redshift type 1a. And here's a high redshift one. This one's about 5 billion light years away. And broadly speaking, they look the same. There's some noise, but that's okay. But this dip is due to calcium, and this dip is due to silicon. And here's some iron, and this is sulfur. So whatever, So when we got data like this, then I was really happy. And now you see the real reason we like to build observatories in Hawaii. I like to go to the beach. Haven't been to Hawaii in a long time because of COVID-19. Plus, we can make the measurements now from home. We can do the Keck observations. But anyway, here's one of these old International Astronomical Union circulars where you report your observations in nearly real time. You can see the date here, October 14th, 1996, and the telescope that was used for the high redshift supernova search team led by Brian Schmidt. And all the Ks are my measurements with the Keck telescopes, okay? Actually, at that time, by that time there were 2 of them. The second one was built in 1995. The first one was 1992. But these measurements I did with one of the Keck telescopes, trying to figure out which one. Doesn't really matter, I guess. It just says the Keck telescope here. Not sure why I said that, because there were 2. But anyway, so the punchline is that here's some of these type 1As, and they're really, really faint. You might say, well, big deal. They're in these scrawny, pathetic-looking galaxies. Obviously, these are really distant galaxies, and so the supernovae should be faint. Here, you can't even see the host galaxy. Maybe a little bit. Well, that's the correct argument. These guys should be faint, but the punchline is that they're fainter than they have any right to be, okay? They're so faint that the derived distances of galaxies are greater than they should have been. So my analogy is with an apple, and I don't have my apple here, but I have a water bottle. If I toss it, right, and I suppose the universe is 1 second old, the apple travels a certain distance, but it's been slowing down because of Earth's gravity. All right, well, if I make Earth's mass less, it'll slow down less, it'll decelerate less, and so it'll travel farther. If there's no gravity, if I remove Earth, it won't decelerate, neglecting Jupiter and the sun and all that. So it gets to an even greater distance. But what we found was that the apple was even farther away than the maximum distance it could have gotten, even had it not been slowing down. So unless there's something weird going on, like dust or something, we had to rule that out, or supernova evolution or something, its dimness might mean that it's farther away, and therefore that the universe accelerated. So that's really bizarre. And I had the privilege of being the first on either team, and I was on both teams at one time or another, for reasons I won't go into right now. But for the high redshift Schmidt team, I announced at a meeting in Los Angeles this was the result. And the editor came up with this headline. We use this term anti-gravity hesitantly because people ask us, can we attach this stuff, whatever it is, to our cars and levitate over, San Francisco Bay Area or Los Angeles or New York traffic jams? And the answer is no. We think that this either a property of space or it's a new type of field of which there's so little that you're never going to collect enough of it. But still, it has an anti-gravitating effect. So that was February of 1998. By December, no one had found anything obviously wrong with our data collection, our measurements, or our analysis, or even our conclusions. So the editors of Science magazine proclaimed this to be the biggest breakthrough of the year. And the caricature of Einstein looks surprised here, not because he's blowing multiple universes out of his pipe. You might not have known that there are multiple universes and they come from the pipes of theoretical physicists. Well, maybe there are multiple universes, but anyway, he's surprised because this one universe is expanding progressively faster with time rather than more and more slowly. He's doubly surprised because there's a sheaf of papers under his arm where there's an equation. The Greek letter lambda equals 8 pi g, Newton's constant, times the density of the vacuum. And you might say, oh man, what a bozo from Berkeley. Why did Dan and others ask me to give this talk? You were taught on your mother's knee that the vacuum is zero, zilch, nothing. How can it have a non-zero density? Well, I'm just the messenger here. This guy came up with it. And he came up with it for the following reason. In 1917, it was thought that the universe is static, neither collapsing nor expanding. And it's true that the nature of the spiral nebulae was not yet known, but the gist of the argument still holds that the universe was thought to be static. And yet, Milky Way galaxy should be pulling on every other galaxy, causing a collapse. So Einstein introduced his cosmological constant of unknown physical origin, no experimental evidence in the laboratory for it, and it had to be finely tuned to not only oppose gravity, but to be the same magnitude. That is, the two arrows are the same size and the net force is zero. That implied the presence of a vacuum energy that was repulsive, a rather repugnant idea to Einstein himself, as well as to many other physicists. 12 years later, when Hubble discovered, along with Lemaitre, the expansion of the universe, the whole physical and philosophical motivation for the cosmological constant vanished. Hubble renounced the idea in 1929 as having been the biggest blunder of his career. Here he is, sad, ever wishing he had never introduced the idea. I don't know that that's what he's thinking, but it might be what he was thinking. Because had he not introduced the idea, he, like some other theorists, Friedman, Lemaitre, Robertson, Walker, could have predicted that the universe is likely to be in some dynamic state. He could have been famous. I'm just joking here. What have we done? The better part of a century later, we reintroduced the cosmological constant, not to give a static universe, but one which over the largest scales accelerates with time. So here in your room, the down arrow dominates. In our solar system, down. In our Milky Way galaxy, down. In our local group, down. But by the time you go out to the Virgo cluster, and certainly by the time you get out to other superclusters, the up arrow dominates and the universe accelerates, okay? So the idea may have been Einstein's greatest triumph, and the only blunder was the arithmetic one of giving it a magnitude exactly the same size as gravity, which would have been, a priori unlikely. So if Einstein were around now to hear our evidence and other evidence, his reaction might have been something like on the cover of, of Science magazine. Well, that's one idea of what's causing the acceleration, but there are other ideas. Perhaps it's not the vacuum energy. Perhaps it's something else, some sort of a new field, like the electromagnetic field, but not the electromagnetic field, just something that permeates space rather than being a property of space itself. And that is generically called dark energy, okay? So the cosmological constant is one candidate for dark energy, but there are many other candidates, and they go by quintessence and k-essence, and even within those things, there are many categories. So there are lots of dark energy theories. But now when you combine the supernova measurements with the cosmic microwave background radiation measurements, and this is corroborated by other evidence, here's the cosmic pie that you get. Dark energy is 70% of all that there is, and we don't know what it is. Dark matter that holds galaxies and clusters of galaxies together, which Fritz Zwicky first mentioned in the 1930s and was roundly ignored or criticized, and then Vera Rubin talked about in the 1970s and was roundly criticized or ignored. Now, of course, these two areas are the hottest or among the hottest areas of modern astrophysics, the study of dark energy and dark matter. Ordinary matter is only 5%, and the easily visible stars and nebulae are only 0.5%. Most of the ordinary matter is actually pretty hard to see. It emits in the ultraviolet or whatever. It's reasonably hot gas in clusters of galaxies, or things that have a filamentary structure in our universe. Anyway, mostly dark energy and dark matter. So that's pretty amazing. So given the importance of the dark energy, the discovery was, and given the corroborative evidence that it amassed by 2011, the 2011 Nobel Prize was given for this discovery to the team leaders, Saul Perlmutter at Berkeley, leader of the Supernova Cosmology Project, Brian Schmidt at the Australian National University, leader of the High Z Supernova Search Team, and then my postdoc at the time, Adam Rees. He's now a professor at Johns Hopkins in your neck of the woods, roughly speaking. But he was my postdoc when we were working with Schmidt's team, and we would talk nearly every day about all this stuff. So I was glad that he was recognized, because he was the first person on Schmidt's team to realize what the data were trying to tell us. But these three gentlemen understood that without the rest of us working in the trenches, the discovery would not have been made. So they invited us to the Nobel ceremony, indeed to the whole Nobel week, which, by the way, this year didn't happen in Stockholm, at least not in any normal way, because they couldn't meet. Even Sweden decided that their experiment didn't work, and now they're sheltering in place more or less. But we got to go in 2011. It was just like nonstop parties and stuff. It was fantastic. And here's the High Z team right after the awarding of the prize to Schmidt and Rees. Here's the Supernova Cosmology project. I should have been in that photo as well, but my primary allegiance was the High Z team. And at that exact moment, we were having our celebratory lunch, and where we could sort of reminisce about how it all was coming to this amazing conclusion. And there my wife presented a consolation prize to all of us who did not technically win the Nobel Prize, even though the Nobel Prize was given for the discovery of the accelerating universe. It was the shirt that I am wearing this evening. Dark energy is the new black. It's limited edition. She sent one to the King of Sweden along with a $2 bill with a note saying, you know, Your Royal Highness, or however she addressed the king, here are two things you are unlikely to already have: a US $2 bill and this t-shirt. Anyway, well, as was mentioned, 5 years ago, all team members were recognized with the Breakthrough Prize, and that was good. I mean, the Nobel just doesn't recognize that big science is done by teams now, but really we all did it. I mean, the recognition is nice, but we all did it because we wanted to contribute something to mankind's understanding of the universe. And at no time as a kid in my wildest dreams did I think that I would ever be associated in such a, especially in such a deep way, with such a fundamental discovery. And that was the ultimate prize, the ultimate thrill. But things like that are good because some funding comes with them and stuff like that. Anyway, to get to the end here, to tell you the surprise, our quest for the past 20 years has been to find out whether the dark energy really is the cosmological constant. And the bottom line is that it's consistent with the cosmological constant, but we're still not sure. So how have we been doing this? Well, here we are at the present time. Here's, the distance between any two clusters of galaxies, let's say, something we call the scale factor. There are wildly different possible futures of the universe. Possible. Here's where the dark energy gets stronger and eventually rips everything apart. Here's where it just keeps doing what it's been doing. Doesn't rip galaxies or clusters of galaxies apart because it doesn't change in its strength with time. And here it actually reverses the expansion because it actually becomes gravitationally attractive. And you might say, well, that's kind of crazy, but there is a historical precedent. The early era of inflation that our universe is thought to have gone through ended because the dark energy-like substance called the inflaton that inflated the universe later decayed into stuff that eventually became us. So all of you contributed to the Big Bang. I like to tell that to my students. But anyway, if today's dark energy does something like that, and if there's enough of it, we could still have a big crunch, okay? So we'd like to know, which will it be? To do that, we can look back into the past, and these curves differ ever so slightly. That's been exaggerated in this diagram that I stole from someone. Don't remember who, that's why there's no credit here, but whatever. Sorry about that. Anyway, there are tiny differences in the past history that will lead to big differences in the future. And that's because the dark energy has only been taking over recently. The universe has only recently been big enough for the cumulative effect of this dark energy to overcome and dominate over the attractive effects of gravity. That's why for most of the history, the curves look nearly the same. And it's only recently that they start sort of moving away from one another. The way we've been trying to do it is by measuring the current rate of expansion really, really well, okay? And here's the surprise. The current rate of expansion is higher than expected. Higher than expected based on what? Well, you've got this cosmic microwave background radiation, and maybe you've had some other speaker tell you about that. But it's the echo or the afterglow of the Big Bang from when the universe was really hot and dense. And it was a uniform temperature, except for a few parts per 100,000 or up to a part per 10,000. There are little tiny variations in temperature that correspond to variations in density. And that's good because those variations in density grew to become galaxies and clusters of galaxies. So we exist because the universe wasn't quite as smooth as a baby's bottom, okay? All right, well, from these measurements and using the standard model of cosmology where the dark energy is lambda, I should have put that in. Make a note to myself for my next talk. CMB plus lambda. Every talk I give, I find things to change. But anyway, assuming the dark energy is the cosmological constant, propagating their measurements or extrapolating, they can come to a prediction. And the Planck data are the best microwave background data up to now. And they predict 67.4 plus or minus 0.5 kilometers per second per million parsecs, okay? I mean, it's just to me, a ridiculously small error bar. That might be their statistical error bar, but I personally have a hard time believing that their systematic errors aren't bigger. But I'm not a microwave background expert, so I don't really know. I have to take them for what they say. And there's other people, checking their work. All right. Previous direct measurements of the local Hubble constant, that is today, were somewhere in the range 70 to 75 plus or minus 4 to 7. So, 70 minus 4 is 66, so that's okay. And 75 minus 7 is 68, so that's okay. So, there's a possible conflict, but it's not clear because the values overlap. The error bars are large, and the error bars themselves are uncertain. Look at that uncertainty in the uncertainty. So more than 15 years ago now, Adam Rees started a project with me and a bunch of others to measure the Hubble constant really, really well. Instead of 70 to 75, what is it? Okay, with a smaller uncertainty. And we do it with our favorite objects, the type 1a supernovae. And we do it by using the Hubble Space Telescope and the Keck Observatory to measure in the host galaxies of type 1a supernovae. You get these really great images with Hubble, and you can find the Cepheid variables. There they are, they're circled. So these are relatively nearby galaxies in which type 1a supernovae have been found. So here's NGC 5584, a reasonably good ground-based image. Clearly a spiral galaxy, okay? But there's the Hubble image. Unbelievable, right? And there are the Cepheids. And you remember that Cepheids are reasonably recognized. So, and the Keck telescope comes in because it turns out that this period luminosity relationship of Cepheids is affected a little bit by the chemical composition. And I took spectra with the Keck telescopes to get the chemical composition. So we could get a little correction factor there. Okay, I want to get to my Q&A. We measured the current rate of expansion. We get 74.0 plus or minus 1.4. We are now writing a paper, which will come out in 2021. I can't tell you our result yet because it's still confidential. Moreover, we're still tweaking it. But I can tell you that it's not inconsistent with this, okay? So the result isn't going away. The Planck measurement, I remind you, is that. There's a conflict at the 4.5 roughly standard deviation level. That means there's a chance in a few 100,000 that this is just a statistical fluke, not indicating something physically interesting about the universe. When you add other techniques, the conflict is 5 standard deviations, even 6. And for particle physicists, like for the Higgs particle, 5 standard deviations is the boundary for what is considered a discovery. So when you take all the stuff into account, we've made a discovery. But even just this result in the Rees paper shows it at 4.4 sigma. Okay. Oh, by the way, if you believe our number, then the age of the universe is 12.8 gigayears, not 13.8. 13.8 is when you use the Planck Hubble constant. So I actually think the universe is a bit younger than what we typically tell reporters and stuff. Then our even later result, more recent, I mean, with a postdoc of mine, he just actually switched jobs. He finished 3 years with me and is now at the University of Hawaii, Thomas de Gege. We measured type 2s. Those are the ones with hydrogen. Now, you can't do the technique as well with type 2s because they're much less standard than 1As and they're harder to standardize. They come from red supergiants. And all of you are familiar with all the attention Betelgeuse was getting last year. Now it appears to be about as bright as it had been. I think, by the way, it just went through several minima. It goes through various periodicities. Several minima just happened to coincide. Moreover, there is this evidence for the Hubble Space Telescope that a dust cloud was formed and blotted it out, part of it out. That's a controversial conclusion because infrared measurements don't show that dust emitting infrared light. So there's a bit of an argument going on now as to why Betelgeuse faded by a factor of 2 last year. Very few of us thought it was about to go supernova. It's not going to happen for 100,000 years, folks. Probably. Could happen tonight. So keep watching Orion. The point is we don't know. But a red supergiant lasts 100,000 or a couple of 100,000 years. And so what are the odds that we're really close to it exploding? Anyway, those are the ones that produce the type 2s. They have an iron core at the end of their lives. Probably Betelgeuse is not there yet because the iron core is in the last day of its life. But then the iron core collapses, the other layers rebound off, and the thing explodes. Anyway, we measured the distances of nearby galaxies that had type 2 supernovae, okay? And we used Cepheid variables. Yay! They're the Cepheids. And here's our Hubble diagram published by de Gege. So this is, distance modulus, but it's just proportional to log distance. I need a left-hand parenthesis, I see here. No, right there, actually. Anyway, and here's redshift, Z. So there we go. There's the Hubble diagram, and it's pretty tight. Here are the residuals compared to a matter 30%, cosmological constant 70% universe. These are pretty good residuals. I mean, a third of a magnitude or so typically. That's big compared to the 1As, but it's better than we'd been able to do with the type 2s before. And our Hubble constant then from the type 2s. And again, the more different types of measurements you make, the more confident you are of a scientific result if you get the same answer. So we get 75.8 plus or minus 5. So we're not very competitive yet on our uncertainty. But still, that agrees with the supernova 1A measurements. And yet it's an independent method. The uncertainty is large, but it will decrease with more time, with more data, including Keck, in the coming years. And Hubble. And Lick, by the way. Remember, Lick. Anyway, other methods also confirm the tension. I had Keck specifically mentioned because I gave an update talk to people who subscribe to the Keck public talks page, and I gave a talk similar to this one. So I wanted to emphasize the Keck measurements there. But here are a bunch of measurements, okay? So here are a bunch basically relating to the cosmic microwave background radiation, okay? 67.4. All right. They're all consistent with 67.4. Those are sort of the distant universe, the early time measurements. Here are today's measurements, including the type 1As, that's SHOES. It's a rather tortured acronym. I forgot what it stands for. Supernovae and the Hubble constant give the equation of state of the universe or something like that. The equation of state is what tells you what the dark energy might or might not be. Anyway, SHOES is us. Holy cow is gravitational lensing of quasars. That's been in the news a lot lately because they get the same result. There's other ways of doing it. They all give values up here, 73. And there's our type 2 supernova point with big error bars, but it's a step. And again, it's a today's measurement, a near field measurement as opposed to a far field measurement. And nominally it agrees with these dudes. So what's going on? Well, the boring thing would be that either the early or late results are wrong. That's still possible. Maybe the microwave background people just completely messed up. I don't know. Or maybe the late time people, like the supernova people, messed up, but I don't think so because there are all these other techniques now, So let's suppose none of the teams is wrong. Then you get to the more interesting, the physically more interesting possibilities. General relativity might be wrong. I don't think so. It's just so beautiful. And it has so many tests. But it might be wrong. And boy, wouldn't that be a discovery? Wow. I'm giving this sort of an increasing probability in my opinion, okay? Non-zero curvature of the universe could give such a discrepancy. The reason I don't believe that is that inflation makes the universe flat looking over the distances that we can see. It's like one gigantic beach ball and you're a little ant, crawling around on that beach ball. So I doubt that it's a non-zero curvature of the universe. Maybe we're in a large low density bubble where the Hubble constant is bigger because the density of stuff is smaller and so there's less deceleration. Astronomers have tried to measure these bubbles and we don't seem to be in one that's big enough. Maybe dark matter is behaving weirdly. Maybe it interacts with light in some weird way. Given that we don't know what dark matter is, this is not a completely outrageous possibility. We're being fooled into this interpretation because we haven't accounted for some weird interaction between the dark matter and the light. Maybe the dark energy is becoming stronger. Maybe there will be a big rip. I don't think so because, again, there are other measurements. We've made measurements that show that at a redshift of 1, the dark energy was not significantly different from what it is now. Not different enough to explain this difference between the two Hubble constants. So I don't know. This is still a possibility, but I don't think so. Now, here's one that I kind of like. Maybe there was an early form of dark energy that gave a boost to the universe. The analogy I give is you're watching some kid's soccer game and you see the soccer ball goes whizzing by you much faster than any one kid is capable of kicking it. So you say, well, what? Is there a single super kid on the team? Or you might say, well, maybe one kid kicked the ball, and then while it was in motion, another one kicked the ball in the same direction, gave it a boost, right? So maybe there was some early form of dark energy, possibly related to the inflaton that inflated the universe, although inflation itself could not have been this boost because it occurred well before galaxies formed. And then the one I kind of like, some particle physicists tell me that I'm deluded, but I kind of like it. There might be a new, and I didn't come up with it, by the way. Other particle physicists came up with it, but a new, very light subatomic particle, a neutrino, a sterile neutrino, because it can't be any one of the three neutrinos that we know about, because otherwise it would affect other experiments that physicists have done. So to not affect those experiments, it has to be what's called sterile. Doesn't really do much of anything. I mean, neutrinos don't interact much to begin with. And if you have a sterile one, it interacts even less. But this would be a type of new stuff that we call dark radiation. It's not matter, it's not dark matter, but it's not dark energy either. It's dark radiation. I don't know. Stay tuned, It's exciting. But to close, how the universe will end, well, we still don't know. Now, this was an article on the cover of Time magazine in 2001, almost 2 decades ago now, about our work. There really should have been a question mark, or how will the universe end? Because even back then, we didn't really know. But now, over the course of 2 decades, we've done more research. And I would argue that not only do we still don't know, but we don't know even to a greater extent in some ways. Because there's this evidence that the Hubble constant is changing in ways we don't know, that we didn't predict. But, suppose the universe just keeps on accelerating faster and faster, then, as I like to joke, if you haven't looked at a galaxy recently, but you really want to do so, you should do it with your telescope or your observatory sometime soon in the next few tens of billions of years, because beyond that time, the acceleration will whisk those galaxies beyond our sight. And so the universe will be really, really dark. I don't have to tell you guys to look at galaxies, because it's quite clear to me that you're a very, very enthusiastic group. You look at galaxies all the time. But anyway, this whole ending sort of reminds me of Robert Frost's famous poem, Fire and Ice, written in 1923, I believe, well before cosmology was well developed. So he couldn't have known about these possibilities, but nevertheless, it goes like this. Some say the world will end in fire. Some say in ice. From what I've tasted of desire, I hold with those who favor fire. But if it had to perish twice, I think I know enough of hate that for destruction, ice is also great and would suffice. So Robert Frost would prefer the big crunch, universe that ends in fire, a passionate universe. But if the universe and he had to perish twice, then eternal expansion and an ending in ice, a cold, dark universe, would have been okay with Robert Frost. And that's perhaps appropriate given his name, Robert Frost. So thank you so much for your attention. And I'll be very, very glad to answer questions. And since I spoke longer than I anticipated, and I gave more details and stuff to you guys because you became clear to me are a really gung-ho club.